Next session will show a workshop on generic programming. So the first talk in this session is going to be given by Walter Svierstra, and he's presenting part of Datatype generic programming in F#.
Okay, thank you very much, Andres. So this is joint work with Ernesto Rodriguez, and Ernesto is a student at Utrecht. He's not at Microsoft Research, as the program says, and he has a strong background in F#, much stronger than my own. So I've picked up quite a lot by osmosis by doing this work with Ernesto. And we teach quite a lot of data type generic programming, quite a lot of Haskell in Utrecht, and he was interested in applying these ideas to F#, and for his master's thesis, and this paper is really the result that we got out of that. So what we'd like to do is, if you look at Haskell, there's plenty of libraries for generic programming there, and what we set out to do is look how we could transfer this technology and these ideas to other languages. And what are the kind of problems that we run into, and how well can we kind of mimic the fancy type level stuff that you can do in Haskell and other languages, and what restrictions do we run into? And in particular, what's really great about generic programming in Haskell is that you're working with the type system to generate kind of a whole family of functions in one go, rather than fighting the type system and, you know, doing all kinds of unsafe coercions and that kind of thing. So we really set out to try to be as type safe as possible. So a little bit of background about F#. So F# is a functional language. It's similar in syntax a little bit to ML. It runs on the .NET platform, which is also shared by C#, which has various implementations, including Mono, which runs on Linux. And it kind of, if you have to describe the language on a very high level, it has a very practical, pragmatic combination of features, which combines both kind of OO classes and the functional features that you're used to. So here's a kind of non-exhaustive list, but it kind of it covers a lot of the features that we'll see throughout this talk. So on the one hand, you have the .NET stuff, where you have classes, you have inheritance, you have a reflection mechanism that you can use to do to generate code or to inspect code, and then you have the usual functional stuff, which draws really from ML. So you have the parametric polymorphism and ad-hoc polymorphism. You have some algebraic data types, pattern matching, and so forth. So the real question is how can we use these features from F# to implement a library for data type generic programming in F#? And that's what we set out to do. So rather than start by answering this question, what I'd like to do is kind of recap on the approach that most libraries for data type generic programming in Haskell take. So as a kind of very small case study, I'll very briefly kind of recap the regular approach to data type generic programming. And there's three key points that we need to address. We need to find a representation type or universe to represent some collection of types. Then we need a methodology for defining functions by induction over this universe. And then finally, we need, well, to make the library practical, we need automatically generated conversion functions, which take some user-defined data type and then converts it to their generic representations that we can run our generic functions and then inspect the results. So how does regular do this? So the regular library, at its heart, it has the usual kind of sum of products representation of data types. So you have a few type constructors like U for unit, K for constant types, I, which refer to recursive occurrences of types, and sums and products. If you want to define a generic function, you typically do this by defining a class. So I might define a class called gsum, where I want to define a function gsum with small g, which takes some value f and then sums up all the integers in that structure and produces an integer. So to define this function, this just declares the function, but to define it, I need several instances for all the type constructors I saw on the previous slide. So I need one which explains that summing up the integers in the unit type returns 0. If I have an a and a b, which are both summable, I can sum the pair of a and b by calling gsum twice and adding the results, and so forth. And then finally, to make this library usable, you need this converting to the generic representation that I mentioned. So this is typically done, so the regular type class here says that in order for us to run these generic functions on some user-defined type, we need a type synonym PF, which is an abbreviation for pattern functor, which corresponds to the representation of a type in terms of sums and products and units and so forth, together with a pair of conversion functions to and from this generic representation. And this instances for this regular class, they're typically generated using template Haskell. So then if I have such an instance for some type, I can then have a sum function which takes an arbitrary value, converts it to its generic representation, runs gsum, and then returns the resulting int. Okay, so this should be pretty familiar. So if we want to port these kind of data type generic programming ideas to F#, we have to address these 3 points. We need to find a way to define a collection of types. We need a methodology for defining functions by induction over this universe. And then finally, we'd like to automate the conversion from user-defined types to this generic representation. So this talk was basically going to try to knock off these 3 points in the context of F#. Okay. So first thing we need to do is we need to define a family of types. And to do that, I'm actually going to use classes rather than data structures. And I'll explain that choice a little bit kind of later on. But for now, trust me that this was a good idea. So what we do is we'll define an abstract class called meta, and it doesn't have any, there's no functions or methods or attributes associated with meta. It's just defining essentially a kind for our representation types. So what we'll now do is we'll introduce several subclasses which are concrete, which are subclasses of meta, which we use to model our little universe. So what do we do is here we can see the kind of definitions we saw a few slides ago for Haskell, where we say we'll take a type U, which inherits from meta, and we'll take a type K, which inherits from meta, and U doesn't have any associated fields or members, and K actually has a member of type X. So there's one little detail that I should point out, is that we have a phantom type argument which we pass around. And this phantom type argument, so phantom type doesn't occur in the body of any of the definitions we see, but we typically use it here to record the type that is actually being represented. And this is information we need during the conversion functions, which I won't go into detail, but it kind of clutters the presentation a little bit. But I thought I'd be honest and keep it in there rather than stripping it out in the slides. So if we want to have sums and products, what do we do? Well, we can look at the identity type, which is the recursive types, where we have an element of this type, tie. For some times, we have an A and a B parameter in addition to this tie. And we have the element we store as a choice. Choice is F# speak for either, if you're a Haskell programmer, so a choice of either an A or a B. Which is stored in the sum class. And there's one crucial thing I should point out, is that both A and B are constrained themselves to be representation types. So this was actually something which was missing from our Haskell definition, where we said, oh, we'll take pairs of things and they can be pairs of anything, but you don't have the guarantee that these pairs are actually representable themselves. So this is a little bit more precise even than the Haskell definition we saw so far. So the obvious question now is, okay, if F# is such a functional language, why didn't you define data structures to represent your universe, like we saw in Haskell? Here I immediately started throwing OO at you, right? And there's a good reason for that. And that has to do with a slightly technical point, but it has to do with the treatment of overloading in F#. So what we'd like to do, if you're kind of immediately try to port these ideas from Haskell to F#, is that you might do something like this, where you define some product type, and you say that this product type takes arguments A and B, where A should have a gsum field or a GSUM member, and B should have a GSUM member, and then I can define this member GSUM for products, which just sums up the left thing and the right thing and returns that. So this is kind of this is the instance for GSUM for products that we saw a few slides ago in the Haskell world, and trying to kind of transliterate that instance definition to F# here by declaring that products, well, provided that both both arguments to the product are G-summable, I can sum the whole product. So this style of generic definition doesn't work so well in F#, and it has to do with the treatment of overloading. So there's a few limitations to the ad hoc overloading or the ad hoc polymorphism mechanism in F#. First of all, you can't have overlapping instances. So this is sometimes something you use typically quite a lot in some of the generic libraries, where you give some universal definition, but oh, by the way, here's one specific instance which will actually trigger some interesting computation. You can't do that. Furthermore, F# has this restriction that it needs to know statically how overloading is going to be resolved. And here, we're kind of very abstract. We're saying, oh, this call here will we'll call the GSUM member on something of type A, but we have no idea what that A is going to be, and F# will complain about this. And so these member functions, which we define post hoc with this extension mechanism, where you can add new members to existing classes or structs, they're not checked when you're solving member constraints. So when you have a constraint like this that you need to solve, somehow it doesn't look at any extensions which you've added post hoc. So that means that kind of these three things put together means that the F# overloading is just much more restrictive than Haskell's type classes, and kind of trying to do generic programming in this style is you're fighting a losing battle, essentially. You're trying to use the ad hoc overloading for something which it was never intended to support. So that's why we use these classes, which works quite well in practice. So the problem is we now need to define kind of this methodology for defining your own generic functions using this representation types that we've seen previously. So the way we're going to do that is, instead of trying to overload use the ad hoc polymorphism that we saw, is we'll provide an abstract class called fold meta, which users can write their own instances of and provide the required definitions to completely define a generic function. And the ingredients we're expecting there is basically the instance definitions that you have in Haskell for the types that form your universe. But there's also a function that we'll provide which serves as a workaround to handle some of the limitations of overloading that we saw previously. So here's the signature. So you can see here that to define the abstract fold meta class, which takes a bunch of inputs and an output and something of type T, you need to give a couple of definitions. So you need to give an instance for sums and products and K and U and ID. And then here's the other one which I mentioned previously, which will work for any meta type. So if we want to define a function like gmap, well, it's not quite gmap because it doesn't update. It's everywhere in the scrap your boilerplate, right? Where you have some function which goes from x to x, and you want to apply this function to all occurrences of values of type x in your data type. The way you do this is you define an instance of fold meta, which will work on things of type T. It takes as additional inputs, it takes something which goes from x to x, and it will return something of type meta. Now all we need to do is come up with the required definitions for the member functions of fold meta, and that corresponds to overriding them and providing some sensible definition. So, for example, the instance for products might look something like this, where we have a product, we have a function, we create a new product, we kind of call fold meta on the elements that we have stored in the product, and then there's two notes that I should point out here, is that we cast the result back to something of type meta. So we have to return a meta, so we cast it to something of type meta. And these recursive calls, so we're assuming that the product has 2 meta values stored there already, so that we can actually make this recursive call passing in a meta value and the function f. So these are 2 things to point out, and I'll get back to both of them later on in the talk, but kind of push them on the stack for now, and then we'll see why this matters later. So for constants, for example, we can actually have multiple definitions. One which says that we can override the existing type declaration, which says for any type A, if you have a constant storing A's, and this f, which mutates x's, just be the identity function and return a meta. But we can also have this definition here, which says, well, if you have a k which is storing something of type x, well, then you should it's very important to apply f to x and then wrap that in a k and then cast it back to a meta. So the override is the one which is required, the one which leaves the value unchanged, and the member of a function is the one which works specifically for the types we're trying to modify. Okay? So what about resolving this overloading? So if you remember, in the product case, we were making recursive calls, and we were making recursive calls on values of type meta. But we only provide specific definitions for sums and products and constants and so forth. And we've provided more than one definition for constants. So there's somewhere there's some overloading being resolved, and how does that happen? And this is where things get a little bit ugly, I guess. We have this extra fold meta argument, which takes any meta as input and an input and then produces an output value. And this is the kind of method we don't want the user to override, but instead something we provide. And it is responsible for handling the overloading. So it'll get a meta, it'll essentially do a kind of a type case, inspect, okay, how was this meta constructed, and then dispatch on the appropriate function. And the implementation is not something I want to put on a slide. It uses a bit of a .NET reflection to inspect the type of its meta argument, and then it calls the method with the most specific type that will still accept this argument. So if you have 2 definitions, as we saw for k, then you choose the one which fits best. So the good news here is that you never have to use reflection. We've managed to trick F# into accepting the kind of overloading behavior that we want. But the bad news is that there's a runtime penalty in every step of execution of a generic function, because every time we want to kind of do another step of the execution, make a recursive call, we have to kind of run our little ugly reflection hand-rolled overloading mechanism to figure out, okay, what kind of meta did I get now, and what function am I going to pass this to? So that's bad news. So that covers the first 2 points, right? We have our representation type, and we have a kind of this methodology through this fold meta class for defining generic functions. And the final thing which is missing is this conversion between user-defined data types and their representation in terms of the meta class. So here, once again, we can exploit reflection. Just as Haskell users use template Haskell, we can use a little bit of .NET reflection to make this go through. So .NET supports quite a lot of nice features. So we have a function like getType, which will just return us the type of a member function getType, which will return us the type of the thing we're calling it on. And F# in particular adds lots of information to the usual .NET reflection mechanism and the usual stuff which is in the type class in .NET for algebraic data types. So it tells you stuff about the constructors that you have available, what their types are, and so forth and so forth. So once again, it's not the kind of code that you want to put on the slide and talk about, but it's all the ingredients are there in order to do this the generic programming that we want. There's a few things to point out is that in contrast to template Haskell, where template Haskell runs at compile time and then generates these conversions for you, and then you can use it in the rest of your code, this reflection in .NET runs at runtime, which means that every time we call a generic function, we have to generate the conversion to to the generic representation, then we have to have this additional runtime penalty when we execute the generic function to handle the overloading. So its performance is not going to be good, I can tell you that already. The code itself is highly untyped. There's lots of kind of manipulation of syntax trees, and there's a lot of boilerplate code in there. And if you try to read through it, you actually need quite a bit of .NET expertise to understand what's going on there. And it's not cross-platform, so a lot of implementations of .NET, they have slightly different names for some of the reflection parts or the F-sharp algebraic data type specific stuff. So it doesn't work, it's not guaranteed to work across different platforms. But, okay, we can soldier on, and we can provide automatically generated conversion functions which will convert to and from our meta type. So that's good. And now we can use the GMAP subclass of the fold meta class to define a GMAP function, which looks like this, where we take an X and an F, we kind of convert, this is the generic thing which will do the conversions to and from the representation type which we generate. Then we call fold meta on X and pass our kind of meta representation. That'll give us a new meta thing which we can then convert back to something of type T using gen.from. So, good news, we've kind of managed to knock off these 3 bullet points. We have a representation type using classes. We have a methodology using, for defining generic functions using this fold meta class, which handles a lot of the tricky overloading for us. And we have automatically generated conversion functions converting user-defined data types to their generic representation. And as a user, if I want to define new generic functions, I don't have to touch any of the reflection stuff at all, right? I just have a few clear definitions I need to provide, and then all the magic happens for us. So if we take stock, we can mimic the regular universe using classic subtyping, and we can really represent the same collection of types in F# as we can in Haskell. And I think it's even slightly nicer in F#, arguably, because if you look at regular, it's actually you have this bunch of these definitions, but there's nothing which binds them together. They just happen to be what the library uses to represent types. And in our library, they're all declared as subtypes of this beta class. So that gives you the guarantee that these are the constructors that we use to generate class, to program our generically, and that's it, right? And this is information which is implicitly kind of floating around in the Haskell definition, but it's not as precise. So we can define these generic functions. They're really untyped. So the generic functions themselves, they typically manipulate all kinds of meta values. And, or they're maybe unityped because kind of everything has type meta. And in particular, it's very easy to make mistakes that if you suppose we have this GMAP function and we have an instance for the constant string, if we return the constant which is storing an int and then cast that to meta, it'll type check. It'll be perfectly fine. But then when we try to kind of unconvert it and back to a user-defined data type, we'll get a runtime error because there'll be an int there when we were expecting a string. Of course, there's an obvious limitation is that this is really useful for defining one class of functions, namely folds over generic, kind of generic folds. Well, where that's a limitation, we can kind of also define several other kind of related classes which are slightly kind of variations on fold meta. So we could take more than one argument, so we can do generic equality, we can generate meta values if we have some kind of unfold meta, and so forth and so forth. So the generating conversions works very smoothly, uses .NET. But once again, they're generated at runtime. So it's worth putting a little bit of thought into if we can do memoization to improve performance here. That when you call a generic function on a type more than once, that you don't go about recomputing the entire conversion kind of class which does the to and from business, but instead just cache that. So then there are some advantages, I think, over approaches like regular. So we've made the definition of a generic function manifest, right? We just have a class, and we can inspect this class and manipulate it and do interesting things with it. So, for example, suppose we want to have a shallow version of the gmap function, which doesn't do much recursion. It just applies the map one level deep. We can do this by taking our existing definition and just overriding the function we have there, which handles the recursion. And instead of making a recursive gmap call, we now just return the identity. So then, and this is actually something which is really hard to do in most generic libraries in Haskell, because they typically piggyback on things like classes, which are not first class in Haskell. So what are the kind of conclusions we've seen is that we can port a lot of these ideas from data type generic programming to F#. But the bad news is, and this is what I said in the beginning, where what I really like about the data type generic programming approach to Haskell is that most of these libraries, they say the types are doing a lot of the heavy lifting for us. And then here, suddenly you're in a situation where you're kind of fighting the type system a little bit, and you're kind of casting everything to meta and then hand-rolling your own overloading system. And so I think it's a nice paper because it illustrates exactly where the differences between the Haskell and F# type systems sit. And I think what the real result is that it provides a lightweight alternative to existing approaches to generic programming that you see in F# nowadays, is that you have certain libraries that do things like pickling, which are entirely generic, but they rely heavily on reflection. And here we've kind of encapsulated all the reflection away from the user, that you can still define your own generic functions and hopefully never have to touch the .NET reflections. A bit of further work. So we could do lots of other clever F# trickery, right? We could use reflection to do static analysis of the compiled assemblies to check that the generic functions we have are actually type safe. Whether you actually want to do that is another question, and it's, once again, it's a lot of hackery, and it'll buy you some safety, but it's the kind of stuff which is really tricky to get right. We could do the memoization of the conversion functions, and maybe this isn't the best way to do data type generic programming. Maybe something more kind of scrap your boilerplatey is more in keeping with subverting the type system rather than embracing it. So how much time do I have left?
3 minutes.
3 minutes. Okay, I'll stop here, and if there aren't too many questions, I can say something about, so I have some backup slides that I can talk about if you want, about Uniplate, so how you can actually implement interfaces like Uniplate on top of this. But yeah, I'll take questions now and give the floor to the discussant. Yeah.
So Tjark is going to be the discussant for this paper.
Good. Yeah, so I think this is a really interesting piece of work, and sort of just for context, I think that sort of people are always quick to say, yeah, so either this is some technique that only works in one language, right, and then sort of use that as a selling point to say, okay, this language is much better than another language, and the opposite of that is the Turing tar pit, right, to say, oh yeah, I mean, you might have this programming techniques, but all languages are equivalent, so I can just implement this technique and do it in another language, and it's all the same, right, and well, in practice, I think we all know that none of these are really true, right? The truth is much more subtle, and I think work like this is very important to actually try to tease out, okay, what are the different pieces, right? And can we adapt programming techniques from one language to another? And if we do so, these are the problems we run into, and these are possible solutions, right? And in some cases, you will even see that, well, maybe I can't do it directly, but I have to use some other features which sort of make it more idiomatic in the other language, right? And so just one other example, I think what people have tried to do is to say, okay, well, Lisp and Scheme are powerful languages because you have all these macro systems, and then try to bolt these macro systems onto other languages, right? And what you find is that this doesn't work so well because a lot of the appeal of scheme macros comes from the fact that you have a very simple language, right? And if you use that in language where you have a much richer class of syntax, then a lot of the appeal goes away. So that brings me to some questions, and I think so you answered already some of them in the talk, and probably you have some backup slides about them. But I would like to know sort of what's the verdict, right? So is this going to be the way to do generic programming in F#? And can we now say, okay, so previously people might have said, okay, the whole generic programming angle, that's a real selling point for Haskell. So can we now say, look, I mean, why do you use Haskell? Why don't you just use F#?
It's hard to say. I think a lot of that is also dependent on the communities that you have. And where I think F# is, I don't know, I can't speak for the F# community, but I get the impression that they're very much driven by kind of pragmatics. Does this work? Is it easy to set up? What's the cost? Whether it's runtime or in using some library or learning something. And I'd argue that the cost here is pretty low, right? In terms of it's pretty lightweight to use, and it kind of just works. Kind of when it works, it'll just kind of magically do this Datatype generic program. Then again, even in languages like Haskell, I'm not sure. I mean, I know this is kind of a faux pas to say in this workshop, but how many people really use generic programming libraries, right? Because you write all these beautiful libraries, but then a lot of people, just use deriving and the compiler built-in ones. They don't rely on kind of any external stuff that doesn't get shipped with the Haskell platform. So it's hard to say. I don't know. I think it's one thing that would hopefully come out of it is it might expose F# people to the ideas from this community, and then be a stepping stone. Maybe there's better ways to do this in F# that we haven't thought of, or maybe there's problems in F# that we're not aware of that could really be nicely addressed using the technology that we talked about this week. But that's future work, I guess.
I see. So maybe one follow-up question. So you already mentioned that you're using like reflection internally, and sort of course, that has a performance penalty. So have you tried to quantify that in some way, or?
No, we should, but
but it's going to be large, right? So
yeah,
no illusions about that.
And what's really bad is that you get a big slowdown. It's kind of so in the generic Haskell world, right? You have a penalty as well. You have this cost of having some time and converting it to its generic representation and running your function and converting it back. But that's like a 2 times linear slowdown, which isn't so bad. If you look at the overloading resolving, it's not linear anymore. It's like every kind of subtree you have to make calls to do this check to figure out which method to dispatch on. And that's really painful, right? For big data structures, that'll be a big slowdown. And I think to be really competitive, that's the kind of thing that we should really get rid of.
And if you had something like template Haskell in F#, would that help? I guess.
Yeah. So that's we've looked actually. So there are some things like that in F# already. You have things like type providers.
Yep.
And one of the things we kind of Ernesto set out to do was say these type providers they run kind of at compile time. So what we could do is we could take I'll write Datatype definition and then write a type provider which generates its representation type, which is like it's not what type providers were meant for, but it has exactly the right kind of ingredients for us to use. But then we ran into just limitations of the existing type provider technology, and that it doesn't cope well with, I think it was writing type providers on generic types, which was disallowed. So then you're kind of at a quandary, right? Do we try to implement this in the F# compiler, or do we work around it for now and then see how far we can get? And we went one way, and then maybe doing this kind of experiment can be useful feedback for
Okay, so I think this is all from my side. So are there any questions from the audience?
Any questions?
So, if you're doing your own overloading resolution, do you even need an intermediate representation of your data? Or do you just do reflection and immediately call the right parts?
Okay, so the question is, if you have your own overloading mechanism anyhow, why do you need this intermediate data type? So what you could do, I think, I'm thinking out loud here, is so you have some data type, and you call a generic function on it, then you inspect the structure of the data type that you have, and then call the right dispatch thing without doing the conversion. That might work. It's not something we've thought of yet, but that might, so doing that would avoid the conversion to the generic representation and then do the dispatch directly. But so you'd still have the problem with this big performance penalty by having this dynamically computed dispatch. But at least you'd get rid of the conversions. Yeah. Okay, that might work, but the instance definitions that you give, they all work. They have to. The type unsafety comes from. I have to return a meta type because I don't know. I don't know the user-defined type that I'm working on, and if you and that's not something I can see that you can get away with easily, because I mean, suppose you have something like a GMap on pairs, right? Even if, and then you have a data type which has two fields, what you do is I'll call the GMap on pairs and then call that method, but then pass in the value of the two fields. But then you'd still need to, when you kind of recursively call GMap, then you need to package up the pairs somehow. And then how would you do that if not by, maybe you could do something clever, right, there by, having some packing and unpacking functions which you remember about and expose to the user or something. Maybe, I don't know. It's something I'd need to think about more. Thanks.
Other questions? I actually did have one. So it's more of a clarification
Sure.
question. Can you go back a few slides?
Yeah?
That was it.
This one? Yeah?
So here you're saying we can only handle folds over generic types. So that, if I understand that correctly, you're not saying that the generic functions you're defining have to be folds on the specific data types, but the recursion on the type argument has to be a fold. Is that correct?
That's the way I put it, yeah. Because that's the way the dispatch works, right? We have a bunch of definitions, and you can make a recursive call on kind of unpeeling one level of meta-ness, and then you dispatch again. But,
so in particular, you have no problems with writing generic producers, is that right?
So I think the problem with generic producers, okay, so yeah, so the GMap is producing a generic value.
Yeah, but so there's still...
Okay, but you have one argument.
Yeah. So often in Haskell for several approaches, I mean for regular not, but for several other approaches, this producer case is always somewhat tricky.
Yeah.
And, I was wondering whether...
We have looked at it. I'd have to check with Ernesto, but the feeling I get is what you could do is you could write a generic producer as something which returns a meta given some seed value, and then you fold you have the fold meta, which is a fold over the representation type, and then that might manipulate the seed value in some interesting way, and then generate values of some meta type, which you can then cast back to the user-defined type. So that I think would work in principle, but I'd have to check with Ernesto.
And then one more. So why regular? Of all the, I mean, how did you Like, did you try 10 things and they all failed, and then regular finally worked?
Okay, so there's different approaches. We looked at a few different libraries. You have some which use GADTs, like replib. And then, of course, F# doesn't have GADTs, so that's maybe not the best approach to try. Regulars, it has the big advantage of being kind of a moderately simple type universe that you're modeling. I mean, if we'd done something like multi-rec, it's easy. I mean, you can see some of the types already get a little bit messy, or quite messy. You want to start something simple. And then the alternatives would be the things like scrap your boilerplate or maybe uniplate. So uniplate is something we can build on top of this, and the scrap your boilerplate is, well, the experiment was also really in comparing.
More thinking into a direction of, like, because you're saying in the very beginning that you're starting to use classes, so
Yeah.
there are libraries like EMGM,
Okay, yeah.
extensible and modular generics for the masses, which also in Haskell are more based on the class mechanism, so perhaps
Yeah.
they would be an easier match.
Maybe, but you can see what kind of what really broke this, so to speak, this approach was the fact that the overloading in F# isn't strong enough to mimic the Haskell classes. So I don't know. Yeah.
All right. So if there are no more questions, let's thank Walter again.
Yep. Thank you.